All right. Well, hello, everybody. I've got the top of the hour, so we are going to go ahead and get started. Good afternoon, everyone. Thank you all so much for joining us today. On behalf of AUVSI, I'm so pleased to welcome you to our webinar this afternoon, From Connectivity to Non-GNSS Positioning and Beyond, Building the Enabling Technologies for Unmanned and Autonomous Systems. My name is Shannon Walker. I am the Director of Programs here at AUVSI, and we'll be your host for this afternoon. And as always, we have a couple of those housekeeping items that we'd like to go over before we jump into our content for today. So as always, the attendee lines will remain muted throughout the webinar. We are recording this afternoon, and a viewing link will be emailed out to all attendees within the next few days. If you're listening and you need any technical assistance, feel free to send a note to the webinar leader using the chat feature at the bottom of the screen, and they will be able to sort out and troubleshoot with you. So we are definitely opening up this discussion for Q&A. So attendees, I encourage you to submit your questions at any time throughout the webinar using the Q&A button at the bottom of your screen. Questions will be saved to be answered towards the end of the program, but we welcome you submitting your questions at any time to ensure that they get in the queue and included in this afternoon's discussion. So the Q&A button is different than the chat button. So just make sure any of those content questions for our speaker today are being submitted using that Q&A button, which can be found alongside that bottom bar. All right, well, let's go ahead and get started. We are so happy to welcome back, and we'd love to thank Elsight for their sponsorship of today's webinar. And we are so happy to have Elsight's co-founder and CTO, Mr. Roee Kashi, here with us today. So I know I am eager to learn more about this. I know you've got a great presentation planned for us. So with that, Roee, I will hand it over to you to kick us off.
Thank you very much, Anna. Um, so, just again, introducing myself. My name is Roee. I'm the co-founder and CTO at Elsight, and I want to focus on what does it mean to be the CTO in Elsight, and why it's so relevant to this webinar here. As part of my role, I'm actually bridging three different lanes, important lanes. One is the head of the product team, and what is the roadmap of our Halo product, and how it fits to the market, and understanding the macro perspective on the market trends and requirements. From another lane, it's understanding our customer needs. It is the onboarding and professional services and support teams, and part of it means that we have direct engagement with our customers and end customers to understand their challenges, understand the pains, create the most difficult integrations to enable their mission eventually. On the third lane is the CTO teams. The CTO team, that means what technology is feasible, what can we solve with technology. So these three lanes of understanding technology and what is the most innovative and advanced technology that can be used with the advantage that we have with our product and our solution that is relevant for the challenges and pain of the industry. This is exactly these three domains that I'm bridging as part of this role. So we're going to present in this webinar exactly how this shift in Elsight goes from connectivity to much broader perspective of connectivity and non-GNSS positioning and beyond. We're going to talk a little bit about the beyond now, and probably in next sessions to deep dive into it. So we're going to focus, of course, on the uncrewed systems in how we enable the mission. And before I continue to talk about Elsight, it's important to understand how the industry evolved so far. When we're talking about the industry, again, on the uncrewed systems, we have the commercial, the civil industry, and we have the defense. and there's a huge shift from commercial to defense. We see it all over, of course, also with AUVSI. And with the defense, it's important to understand that the budget of the defense defense offices in different places in the world, in the UK and USA, and of course NATO and in Japan, are increasing significantly. Also, the investment in uncrewed systems is increasing, not linear, exponential growth. So we're seeing a huge demand for uncrewed systems and for solutions for uncrewed systems for defense market, and it goes back to commercial market and homeland security, like the drones, first responders, and drone in the boxes, and for surveillance, and also to the pure commercial solutions. So we're seeing this growth and maturity in the industry. And as part of this, when we're talking about defense, then it's especially in events like we have recently started with Ukraine and Russia, and continue with different places in the world, we see accelerated R&D paths, processes, that things that typically could take years now moving in months, and sometimes in weeks. So talking about Elsight specifically, again, those who knew Elsight from previously, our model was always to provide a connection confidence and to provide resilience connectivity. Now it's bigger. We're talking about resilient mission completion technologies for uncrewed systems. And I'm going to talk about this kind of a reason to increase the value chain here. So in this webinar, I'm going to again focus on connectivity and positioning specifically for UAVs, UGVs, and USVs. They all share the same requirements here. At Elsight, we already have more than 10,000 of our Halo units deployed. We accumulated over 500,000 operational hours in real-life scenarios, and not just testing. We have more than 100 different OEM partners worldwide, and we recently had a lot of success also on the defense evaluations, specifically with the if we're just talking about the US DOW, we have TRN9 evaluations and assessments with the SOCOM, with DAU, with the 75th Rangers Regiment, and as part of the Project DI, DRM2, we're all in phase 3, and very successful TRX-LT event, first of its kind, and hopefully we could share more about it very soon. Speaking of the, just to start as part of the agenda, I want to explain about the connectivity challenge, about our Halo solution, and then how it's connected to the non-GNSS positioning. So starting with the connectivity, the traditional way of how the typical soldier or the officer would communicate with a UGV or UAV or USV is with a line of sight based radio, and it has a lot of different challenges. One is the operator exposure, because if you need to be in line of sight, you need to be in the area of conflict. If it's a police officer that arrives to a certain scene to operate the drone or the robot, or if it's the soldier that needs to be in a battlefield in the front line in order to operate the drone, again, it's putting the pilot at risk. And then if we want to go and fly or operate the platform to long distances, it means that we need to deploy more relays and repeaters, and it takes a long time. Of course, with all that, we're still gonna have effectively a range limitation. If it's because of the radio signal, if it's because the terrain constraint, and if we're talking about the flight path constraints, then it's very challenging to use line-of-base radio and for example, fly or operate a platform behind hill or below the tree line, below the rooftops. It's something that is not part of the concept of operations of line of sight based radios. And then when we're talking about scenarios where you want to stay stealth, line of sight based solution is not the ideal solution here, because it requires flying in high altitude, and then it's more exposed and vulnerable to radars. It means it needs to transmit in high power, and then it makes it more vulnerable to RF scanners. So there's a lot of challenges when we're talking about having multiple relying only on line of sight based radio. But what we're saying is that we don't need to remove the line of sight or replace it with something else. But what we want to do is to enhance it and really create a solution where the platform can utilize every bit of available spectrum. And this is what we see as a new paradigm now. We see that platforms that are utilizing private LTE and 5G and commercial LTE and 5G from and also connected with from multiple different carriers, and also connected with the line of sight based radio, connected with satellite. We see how everything is now taking the shape of utilizing more communication paths, more different technologies, different bands, different carriers. And the idea here is how to do this right, how to create a resilient communication solution that is able to adapt, that is able to hand off between the different communication paths, the ability to have a logical pipe that encapsulates both commercial networks and WAN-facing networks, like internet-based networks, and combine it with point-to-point managed mesh radios. And how again to put it in one logical pipe to allow these seamless handoffs between cellular networks, for example, being aware of latency, being aware of high quality, being aware of how to provide it with high security. So this is really the bread and butter of Elsight. When we're talking about the connectivity solution, when we're providing a logical pipe that is able to utilize every bit of available spectrum, different communication paths, different technologies, different bands, we were able to use also commercial LTE and 5G securely. We're able to use commercial solutions of satellite, for example. And then what we gain is, first of all, we unlock the potential of the concept of operations of flying with no distance limit. We're able to have a pilot that, instead of being in the field, the pilot can be in a remote control center. We shorten the deployment time. Wherever we have a commercial network available, we can just deploy our system and start flying or driving around. We don't need any relays and repeaters to prepare. Again, no effective distance limit. The bottleneck now is not the communication. The bottleneck would be the battery or the fuel, but basically, comms-wise, you're unlimited as long as there's any kind of availability from any type of communication path. And then there is no line of sight constraints. The entire concept of operations today, of operating platform, was built around the limitation of line of sight. When we don't have this limitation, we actually get a new concept of operation. It means that we're now able to operate platforms beyond wheels, beyond hills. We can also land remotely and fly again. We can then behind the trees. We can go below rooftops and tree line. So this is again changing the concepts from all around. As part of this is also how this platform can be seen from the other side, because again the line of sight based constraints created the concepts of flying in high altitude and transmitting high power, which also in turn, this is how counter UAS solutions were designed to. But with this solution, drones can fly in low altitude because they're communicating with the terrestrial cellular networks, for example. They're able to transmit in low power. We're talking about cellular communication. The transmission power is about 200 milliwatts. So it's almost flying in stealth mode. So the idea here basically is utilizing all the available radio spectrum, again, to create this resiliency, and again, being aware of security, how to do this right, and how to provide low latency and high resiliency. But one of the understanding is that even the perfect connectivity solution is still not enough. When we're talking about resiliency, then it's not enough to talk about the resiliency of communication, because eventually what we want to ensure is mission completion. And again, what we're seeing here, the perfect component in a broken system is still a failure. So what we're trying to do now, and again, from understanding from the technology aspect, what can we do from the product perspective? What is the relevance to our product, and what can be, what makes sense to be part of the product? And from our customers and support, understanding where are the pains and challenges. We understand that position is a huge challenge. We understand that video is still a challenge. And we understand that autonomy is a challenge. But we're also understanding that every uncrewed system today is built almost entirely on 4 technology pillars: connectivity, video, position, autonomy. And they all work as 4 different siloed pillars. You'll integrate the connectivity solution, and then from different places you will integrate a completely siloed and dedicated video solution, and then you'll have a different and siloed positioning solution, and you'll have the autonomy solution, and each one is doing its best to be to make this pillar, this lane working perfectly. But there's no one fabric, there's no one layer, there's no one bridge that connects all these four different pillars into one shared state and understanding and ability to cross-reference and contribute to each other. And this is why we came up with the understanding that that's a critical missing piece in the uncrewed systems industry, and we named it IMSU as the concept, the integrated mission suite for uncrewed systems. And the entire idea here is to create a unified policy layer that connects these pillars into what we call a mission-aware system. And it sounds like huge, buzzwords, but it comes into something that is pretty concrete. We want to create a shared state, so every pillar, the connectivity, positioning, video, and autonomy, can have its own metrics. It can be exposed to a shared state, and then we can use, if there's information that can be relevant, same information that can be arrived from different sources, we can cross-reference this output and understand which one is the correct one. We can have a unified policy that governs the platform behavior. For example, if in some segments of the mission it's expected not to have communication, then we can continue, the platform should continue with its course. If it's in some area we don't have the connectivity, but we want to have the connectivity, there are things that we can do in order to regain this connectivity. If in some places we activated a AI assist, for example, in order to move to a certain target autonomously, then it's expected in terms of connectivity that even if we lose connection, then we can continue with the AA assist. We know that if there's a bottleneck on the connectivity and it's starting to get low quality or low bandwidth, then we can reflect it to the video pillar to reduce the quality. So there's a lot of things on what does it mean to have a shared state here. I want to focus on positioning in this and positioning in this webinar and the connection between GNSS and between positioning, GNSS positioning and connectivity here. And it's important to understand that today it's no longer considered as if one day there's going to be a problem, but this is the primary and default assumption that GNSS in a lot of different deployments, it's not something you can rely on, or at least not solely rely on a GNSS positioning solution. So this is the baseline assumption, and when we're talking about critical infrastructure and contested commercial environments, this is also something that is spreading fast. Today, the GNSS spoofing and jamming is not the top challenge for commercial deliveries, for example, but in places that is frequently affected by GPS jamming and spoofing, the CAAs also want to have a safety net, a safety solution that if there's a jamming or if there is a spoofing on the GNSS solution in that area, how we can safely terminate and abort the missions. So we're going to talk about this as well. And then it's important to understand that when we're talking about position, it is not binary. It's not either we have it or not, but we're talking about a spectrum of accuracy and confidence. So the more inputs we have in order to correlate it, in order to improve it, in order to understand where it's correct and where it's not, it allows us more methods to use it when needed. Today actually it's the first launch or almost pre-launch of the Elsight new cellular based non-GNSS positioning. So I want to focus here to talk about what does it mean, what can we achieve with this non-GNSS positioning, and how does it actually work. I'd say that this is a new Elsight product and it's bundled on the same Halo hardware that we currently have. So it's really bundling the connectivity solution with the non-GNSS positioning together with a video offering and exposing interface to platform manufacturers so their autonomy layer can get and set a lot of this information. So when we're talking about this connection between connectivity and non-GNSS positioning, this is actually where this magic happens, because it is much more linked than what most systems recognize. On our Halo, for example, we have 4 LTE or 5G modems, and they're constantly interacting with cellular infrastructure because it's part of the main job of the Halo to create this beyond line of sight connectivity with LTE and 5G or 3G, and it's communicating with cellular infrastructure that is static and it has a known physical location, and this interaction alone creates positioning data, and this positioning data is today mostly ignored in many systems that might have a cellular modem on it. It will be used solely for connectivity, and we completely ignored the potential information there for positioning. But again, the connectivity and positioning are not an actual separate two problems. They are two expressions of the same infrastructure. The infrastructure in this case is the radio spectrum, and with the cellular towers, one expression is to use it for connectivity, another expression is to use it for positioning. Again, when we're talking about IMSU, we're trying to show how different pillars may have contributions, each one to each other. So let's start with a concrete example of IMSU in action, let's call it. When the positioning pillar fails, and the positioning pillar in this case is when the GNSS fails, let's call it our the traditional way of getting location, then from the connectivity pillar, we're studying where we can get enhanced information that will allow us to provide an accurate position. So it means that we'll need to first of all calculate the cellular base position of the platform. Second, we will need to share this positioning data with the autonomy layer and or the remote operator. So for example, if we have connectivity, then we can send this location to operator to see it on a live map, like to track the platform. And if we don't have connection, we can still provide it offline, on edge, send it to the autonomy layer. So every platform manufacturer can get this information of what is the current cellular-based position and use it in order to continue with this course or to safely go back home, or to use it to regain connectivity. We'll talk about this later. The third thing is the ability to use the cellular-based location in order to trust GNSS. In communications that we had with different OEM partners, different platform manufacturers, they said that in environments that have often GNSS spoofing, they don't use GNSS at all because they can't tell when the GNSS is accurate and when it's not. And if they use the GNSS when it's spoofed, then the platform can just might crash completely. And then just by using this cross-reference of telling when using the cellular-based position that we have, telling when the GNSS is accurate and when it is spoofed, solely by this, your platforms are able to start and use GNSS when it's available. So let's talk a little bit about the top 3 challenges of having cellular-based positioning working. First, there is no trusted base station data. Even though it is, cellular towers has the fixed location, still there isn't any trusted, reliable database, and then it makes it pretty challenging to create this kind of solution when you don't know the location of the cellular towers. The second thing is that when a modem is creating this spectrum scan in order to understand what towers are available around, it takes a lot of time. This scan is limited to this time is limited to different bands and RATs and the radio access technologies. And then, for example, you need to go through each radio access technology like 3G, 4G, 5G, and then go through all the bands and then through all the channels in each band. Then you need to wait for all kinds of different handshake intervals and broadcast intervals in order to make sure you actually see the tower in that channel, and it takes a lot of time. And when we're talking about platforms on the move, then it's this method is almost unusable at all. The third thing is when we're talking about the traditional way of creating this kind of a positioning with RSSI triangulation, then in order to get something that is reasonable in terms of actually use it, we need to see a lot of towers. And when we get just a small number of towers, what we get is very low accuracy, very noisy information. Okay. So if you're talking about Elsight solution, how we mitigating these challenges, the first thing, we got huge validated worldwide base station locations database. We already have collaborations with MNOs around the world. With a lot of MNOs, we already get the APIs and information of the actual validated locations of the cell towers. And in other places, we're providing our self-learning as part of the Halo and non-GNSS positioning. We also introduced the self-learning towers locations. It means that on each and every operation with, again, UGV, USV, or UEV in a certain area, we automatically record our statistics. We automatically record the timing information, to understand, to estimate the distance and the position of the drone correlated to the cellular towers. And when we have an alternative positioning source, we can create the reverse action and learn the location of the nearby cellular towers. This is important for, of course, non-cooperative networks, and this is how every customer can create and enhance the database by itself. And then when there's when it's completely, there's no additional information and there's no option for creating this kind of learning missions, then the user can also import manually this information. And then as part of our data and as part of our flight hours and missions that we already have and the recorded data, we continuously able to validate this information, because on every mission that we have, the Halo can just have more information, more location information, and can cross-reference what we're seeing now versus what we believe should be the right location. The second thing is that when we're talking about scanning, then it takes a lot of time, but if we distribute it to 4 modems, and each modem is now doing this scan, but not on the entire spectrum, but each modem carefully selects the specific bands that we know that are relevant for that region, we're now getting 4 times of the most accurate channels that needs to be scanned in that area. So this is continuously and dynamically updated per the location of the platform. And then the third thing is that there are multiple different methods of how to get a reliable cellular position. In one method is using the LTE and 5G timing advance parameter. It's a parameter that is part of the core protocol of LTE and 5G that allows the device to talk in the right time with the cellular tower. I mean, when we're talking about time division, we have multiple different devices. Each device that communicates with the cellular tower has exact timing when it's allowed to speak. In order to make it accurate, then the tower informs the device, or the cell base station informs the device if they need to communicate, start and speak and return a few nanoseconds before the actual turn. This timing parameter can be converted to distance information. Distance information with multiple different modems at the same time is converted to actual geolocation. And then another method would be to use the signal parameters that we have from the serving cell that we're communicating with, not just the timing advance parameter, but the RSSI and RSRP and RSIQ. This information can help us understand more about the distance between the platform and the cell tower. But for every serving cell that we're connected to, we also have the available neighbor cells. This information is immediate. We don't need to do any scan in order to find it. And then on the last point, it's the ability to have a short and dedicated scan for the different sites to get more information and ability to fuse all these different methods in order to get one understanding of what is the most accurate, or the position that makes the most sense. This is what provides us this kind of advantage. And with the fourth one, this is pretty important because we already have a lot of recorded signal data, and it is fused with the platform position. If it's a drone, it's also with the pitch, yaw, and roll. And we have all this information that allows us to train model much better. Because eventually, when we're talking about the movement of the platform, then we can understand the movement pattern. We can understand the constraints. So it's not like every point that we need to understand what's the location, we're starting from scratch. But the correlation is actually what are the different towers that we see, the distances, and another overlapping section, let's call it, which is where physically can this platform be given the time that passed between the previous location and now. So having this understanding of learning the platform movements, learning from our data how to correlate the signal and the timing advance and the information that we see together with the actual position provides a significant advantage in this case. And again, when we're talking about best practices, I would suggest these kind of 4 best practices in order to create a non-GNSS cellular-based solution. Now we're talking about the connectivity here, that it has 2 functions actually. So one, when we're talking about the online mode, when we have a working connection, then the Halo on the platform can understand the RF, collect the relevant RF parameters and the cellular parameters, send it to the server. The server can now create the calculate the position and send it to the operator. And then the operator can now see the locations in real time as part of the GCS or in a different map, and update the mission when relevant. And the offline mode, then it means that we're using the connectivity either in maintenance mode before the mission or during a mission. We use the connectivity in order to synchronize the database that we have on the towers and the models that we train from the server to the Halo, and then the Halo can complete the calculation, the positioning, and run the entire positioning algorithm locally on the edge with no additional connection. And then in order to use this connection offline, we can the Halo expose this positioning either through API or through standard protocols like Mavlink, or even to create an NMEA-like protocol to make it compatible with any kind of platform. So let's now talk about the second use case of IMSU in the connection between connectivity and positioning, and it's what happens when the connectivity pillar fails and how positioning can step in for this. So first, because the Halo already holds the information on all the nearby available cellular base stations for the positioning, then we can use it to understand what are the nearby cellular towers that the Halo can connect to when the relevant SIM cards that I have. So if I know that I have a SIM card of T-Mobile, for example, and we lost connection, but I know that there's a T-Mobile cellular tower in 2 kilometers at one location, and there is an AT&T cellular infrastructure 5 kilometers to another direction, and I know there's a Verizon cellular tower at the other in another area. This information again can be shared with the platform manufacturer Autonomy layer, so the platform can navigate using the positioning. When positioning is available, we use the positioning in order to regain connectivity, again with the same data set. In places where we're talking about smaller platforms, direct connection between Halo and Autopilot, then Halo can also instruct the Autopilot to navigate to the place with possible connectivity paths. Just to show a little bit how it looks like, as part of the Elsight dashboard, we still didn't launch it. We're gonna announce official launch later, but this is currently as part of the pre-launch. I'm showing it first here. What we got here is 3 different lines of the same device. One is the GNSS location, one is only the cell location using timing advanced parameters from the connected towers, and the third line is using RSSI based information. You can see how accurate it is. This is not something that is guaranteed, this accuracy in every environment. Of course, it depends on how much towers we have, if we know all the towers in advance, but today we have a huge database of cell towers because a lot of operations we have and a lot of collaborations with MNOs, so we feel very comfortable with this solution. I want to close this webinar again with talking about the IMSU, again, Integrated Mission Suite for UXVs. And the entirety here is to provide the one voice, the unified policy, this layer that its mission is to create resilient mission completion. This is really the entire concept here. In this webinar, we focused on the example of connection between connectivity and positioning, but it goes to different examples on the connection between connectivity and video and positioning, and connectivity and position and autonomy, and so on and so forth. This solution works and deployed on UGVs, on UAVs, on USVs, and again talking about the connectivity to positioning. When GNSS fails, the cell infrastructure provided positioning. When we have positioning and autonomy, we get connectivity. Yeah, when the comms fail, and we have positioning working, and then we can navigate the platform to a place to recover the connection. The ability to have this cross-validation and allow each pillar to contribute and to enhance others, this is one of the core engines of what we call the IMSU concept. Thank you very much, and I'm here for questions.
Right. Wonderful. Well, gosh, thanks for an excellent presentation. We already have a couple of questions coming in from the audience. Attendees, as a reminder, if you do have a question you'd like to submit, go ahead and do that using the Q&A button at the bottom of the screen, and we will add them to the queue. We'll get through as many as we can over the next, 15 minutes or so. All right, well, let's go ahead and jump right in. So, question came in, and it says, in our deployment, the satellite terminal can't get a link when GNSS is jammed. Can, your solution help with that?
Yes, I mean, we have exactly this kind of deployment today. As part of the of this feature of this product, actually, we also implemented APIs with different satellite terminals, and we have deployments where we're using the cellular-based location and inject it to the satellite terminal in order to get a working link.
Wonderful, thank you. Another question came in. It said there's a few other players, already offering non-GNSS technology for navigation, as I'm sure you're aware. How does your technology compare to these other players, and what's the value add of customers, buying non-GNSS from you versus a competitor?
Yeah, so it's a great question. So there are many non-GNSS positioning solutions. There's some that are visual based. There are some are sky polarization based solution or stars or all kinds of different options. This solution, it mainly talks about the relative advantage that we have with bundling the connectivity with non-GNSS. And specifically when we're talking about our advantage, the first and foremost advantage is our focus in our attention to uncrewed systems. So cellular-based position can work pretty good on stationary places. If you just want to have a stationary place, you're not moving, you can have 5 minutes of scanning what you have around and then try to get a position. But also, you could, for example, send it to Google API and get information, but it's not kind of solution that is relevant for on-the-move platforms and for defense or on-premises solutions.
All right, thank you for that. We did receive a question about swarms. So it said, recent media reports included a description of swarms of hundreds of UAV in a single deployment. How many UAV can be used in a single theater?
Yeah, it's interesting. We have this concept of, first of all, of swarm-based connectivity, and it talks about the advantage of creating a resilient connectivity in a group of, like a swarm, a group of multiple different platforms. And as part of this ability, we're able to, when there's a point-to-point network, mesh network between the nodes in this swarm, then we're able to jump between different platforms and use the shared bandwidth, the shared backhauling, let's call it, of the entire group, and allow each node to send it through other nodes. When we're talking about specifically how many UVs can be used in a single mission, let's call it, then this is also very interesting because normally when we're talking about the line of sight based radios, then it's limited to quite a few because in line of sight, each platform needs to have again its own frequency, and they all need to share the same band. They need to communicate with the pilot, and if again you want to have swarm-based mission, then either you're gonna have a lot of pilots in the field, or that you have this kind of swarm-based mission. Again, everything handled from the field. When we're talking about Halo or any concept where you're able to utilize a much wider available spectrum, including including cellular-based solution, commercial and satellite and things like that, then you can go beyond line of sight, and it means that you can run effectively 100 platforms at once and operate everything from the control center. So it just makes it much more easier. Combine it with positioning allows each of the platform in the swarm understand its location and expose it to others in the group.
Fascinating. Thank you so much. All right. The next question that's come in asks, in your presentation, you mentioned that Elsight is addressing the connectivity and now the positioning integrity. Can you speak at all to how you'll address the video and the autonomy integrity?
Yes, I don't want to spoil it too much from next launches. There's a lot to expect here. I would just say that I'll say two things. First of all, video is a lot. It's one thing to provide the video to the operator, and there's the ability to use video in order to detect targets and to allow the user to choose a certain target that it wants to continue and move to and track this target, for example. And then when we have the video and when we have the video and we have the autonomy and we have the AA assist, then when we lose connectivity and when we lose positioning, the video and autonomy can continue to enable the mission. So again, we're talking about mission enablement. We're talking about how 2 or 3 pillars provide us complete and provide us like a backup to the 4th one. So video and autonomy, basically we're talking about connectivity, positioning, video and autonomy, they all provide this mission enablement with different combinations.
Awesome. Well, it sounds like there are some exciting things coming down the line for that. All right. Moving on, another question that's come in has asked, when the drone is moving and it hands off to a new cell tower, how long does it actually take to get a reliable position fix from that new tower? And then during any gap that there is, does the autonomy side just kind of fly blind, or is there something that helps to keep it stable?
Yeah, so the moment that we see a new tower, not just when a new tower, but the moment that we're able to see the new tower or an update in the timing advance or an update in the RSSI, things like that, we instantly get this position. Again, when we're talking about doing it on the edge, all the information is on the Halo itself. We don't need any API to Google Maps or to any server. Everything is done locally. Part of the solution is how to securely send this information when the connectivity is available from the server to the Halo, and then from the first moment we have any kind of information from the cellular towers, we instantly get a position. Depends on the number of towers, the accuracy can be changed, but that's how it works.
Perfect. Another question about the benefits of using this product and going with Elsight. So, what is the incentive for customers to buy a suite of the comms, navigation, video, autonomy from Elsight versus going best of breed for each of those components?
It's the best practice is to get the best of breed for each component. What we want to show here is not use our managed point-to-point radio. We don't produce any. We don't provide our own satellite terminal. We don't provide our own video encoders or video IP cameras. What we want to show is with the right integration, and my cat wants to say it too, with the right integration, we can create an abstract layer between the halo and the and with external connected integrated devices to create this shared state. So, for example, instead of configuring the bitrate and the video parameters on the IP camera, you would set it on the Halo device. In places where you have limitations, integration limitations, for example, for low SWaP-C integrations where you cannot add an additional video encoder, then it will be the most common decision probably to use our own video encoding. So you would just connect a USB camera and use a video feature to send the data, to send the video, to compress the video, of course, encode it, and it will be correlated with the connectivity immediately. Okay, in terms of having adaptive bitrate. Again, talking about the navigation or comms or autonomy. Today we don't provide any, we don't develop our own autonomy feature, but because we're able to host third-party services, we're able to load them on the same Halo platform and create this bridging layer between the autonomy or the video or the comms to this IMSU brain, let's call it, to create this mission enablement, as we call it.
Amazing. Perfect. Thank you. All right. We have lots of questions coming in, so I'm going to keep going through them. Another one says, you showed that RSI-based positioning is more accurate than timing advance alone. But how does that hold up in a dense urban environment where you would have a lot of multipath interference, and asking, does the signal bouncing off buildings actually break the location estimate?
So it's not that RSSI-based positioning is more accurate than timing advance, but it's the RSSI-based positioning together with timing advance is more accurate than timing advance alone. The fusion is always better. But specifically when we're talking about interferences, then it depends on, the more information allows us to understand what makes sense or not. Just as an example, when we're talking about multipath interference, then sometimes we don't know if the path is bounces off a building, for example, or in line of sight. But if we have more information on what's the available sites, then there is one position that is the most that makes sense the most, because if it would be in one option where it has line of sight, then it should have seen also this and that tower. But if we don't see these towers, then it's probably in another direction. Again, when we're talking about uncrewed systems, then in some situations these problems are relevant, because drones probably will have the line of sight, direct line of sight with the cell towers. Again, in most cases, not always, but again, the whole idea is to find what is the most reasonable location that can work.
Perfect. That was a great clarification. Thank you for that. I'm watching our time. We only have 2 minutes, and we have more questions left than we're going to be able to get to. So attendees, if we don't get to your question, just know that we're going to be sharing it with the Elsight team, and they will plan to do some communication directly afterwards. So I think one of the last questions we're going to have time for today asks, how do you communicate in remote conflict areas with no cell towers or no satellite connections?
When there's nothing, there's nothing. But the whole idea here is to understand what's the mission. And if there's an area where there's no cellular towers, that's okay. When there's no cellular towers, that's okay. But if we know that in a certain segment of the mission we should have something, then when the positioning is available, we can help the platform arrive to the place that we will have communication. So this is really the idea here, and I will add that in order to understand the position of the platform just with RSSI based option, we don't even need to have a SIM card, and we don't need to actually connect with the cellular towers, but just with the 4 modems and the ability to have direct scanning, this is enough.
Perfect. And with that, we are at the top of the hour. I'm so sorry we didn't get to answer everything, but great audience engagement. Thank you, attendees, for all of your questions that you submitted today. And like I said, if we did not get to your question here live today, they're definitely going to be passed to the Elsight team to be addressed after this webinar. So in closing, on behalf of AUVSI, thank you so much to you, Roee, for spending your evening with us, and for the Elsight team for their support of today's webinar. Attendees, as a reminder, you are going to receive a link to access today's recording within the next couple of days. All of the recordings are available on AUVSI's learning and engagement platform, Able. If you have any questions or comments for our team, please feel free to reach out to us at education@auvsi.org. And lastly, today's program is copyrighted by AUVSI with all rights reserved. So with that, thank you once again, Roee, for your time today. Thank you to Elsight. Thank you, attendees, for being with us today. We hope everybody has a wonderful rest of their day. Thank you.
For having me. Bye.